Well, good morning, everybody. Thank you for joining Lock and Learn, a flexible opportunity brought to you by Johnstone Supply to get you guys through our COVID-19 relief project. So what we're going to be discussing today is we're going to be going through one of our CEU classes on compressors and talking about compressor technologies and how they've changed over time and getting an understanding of how they're actually functioning. Because we do have a variety of different styles of compressors in our industry. Most of us in the residential HVAC industry are really only going to know probably a couple, maybe three, but I want to go over the different styles that we have even into our commercial refrigeration and some of our older AC and refrigeration systems. So our main objectives are to explain the functions of a compressor inside of a refrigeration system. We're going to talk about compression ratio because not too many times do we actually talk about compression ratio and the capabilities of a compressor. We'll talk about four primary different methods of compression. We're actually probably going to be going into a fifth one on a separate presentation. We're going to state specific conditions under which a compressor is expected to operate and the things that it is not capable of doing. We're going to go through differences between hermetic compressors, semi-hermetic compressors. We'll actually talk about scrolls, and then we'll move into a little bit about, some like the Daikin swing style compressors. So we're going to describe various working parts of a reciprocating compressor and just to get to know the functionality and the design of the different vapor pumps that we work with. So the function of a compressor, and it's any compressor. So when we start talking about fundamentals of refrigeration, we're looking at a refrigeration process, just like Jeff was talking about yesterday. Any refrigeration cycle has four primary components: a condenser, a compressor, a metering device, and a vapor pump. And that's all our compressor is a vapor pump. And sometimes we use different types of locomotive force to drive those vapor pumps, but it is just a vapor pump. So it increases the suction pressure to a level that is, to whatever our level of discharge pressure is. So the compressor increases pressure and corresponding saturation temperature or boiling point of the refrigerant vapor to high enough levels so that the refrigerant can condense and reject its heat back through the condenser. So its purpose is to increase the pressure. What a lot of people don't understand is it's designed to increase at a specific ratio, at a specific capacity when we're talking about single speed compressors, which a lot of the compressors that we've encountered have been single speed. We're now moving into multi-staging and multi-speeds and variable speeds, and that kind of shifts the capability of the compressor. But if we're just primarily talking about functions of single speed compressors, then we're going to be looking at the design capacity and the design envelopes for those. So if we take a fundamental refrigeration class and we apply it to our residential, commercial, industrial, if we apply it to HVAC, we're really looking at a very simple refrigeration process that is going to use common types of materials. We're going to use common types of condenser coils, common types of evaporator coils. We're going to use fans to move air across our condenser, and we're going to use fans to move air across our evaporator. But when we talk about principles of refrigeration, it could really be any means of transferring and moving heat across those elements, right? Because if we were talking about this exact same principle, so we look at let me grab my Sharpie and we'll walk through our process. If we look at the process happening inside of our vapor pump, so we are going to bring a low pressure gas into our vapor pump, right? And then we're going to compress that gas to a certain ratio. And we're going to now increase the capability of that vapor because we're going to increase its temperature, which means their pressure. It's going to increase its temperature. We're going to get it to a point where we can now have the opportunity to cool that compressed vapor. And as we move it through our condenser, we're going to convert from a vapor back down to a liquid, right? So we've moved air across that condenser that is cooler than our vapor temperature. So we allow that temperature to drop. We maintain pressure, but we allow our temperature to drop. And as we do that, we condense from a vapor back down into a liquid. As our liquid hits our metering device, and remember, we need to be completely liquid, because if I pass vapor through my metering device, I'm not doing any work with it. I have lost capacity. So I have to have a nice solid stream of liquid to my metering device, which is why we do subcooling. We make sure that we back our liquid up in that condenser a little bit so that the refrigerant hitting our metering device is completely liquid. So when we come through our metering device, whatever kind of metering device, whether it's a TXV, an EEV, whether it's a fixed orifice piston, a capillary tube, all we're going to do is we're going to, when we were talking about resistance in our electrical classes, we talked about changing the flow. Well, what we're going to do is we're going to change some of that capacity flowing through there. We're going to restrict the flow of our refrigerant so that we can simply change the pressure. We're going to try to maintain our volume that is passing in that system, but we're going to reduce the pressure at that point. So when we hit our metering device, if it's an expansion valve, we're typically going to flash through there at about a 25%, 75% mixture out of our metering device. So we're going to have a liquid that is starting to already be dispersed as it hits our evaporator, but it's still liquid form, still liquid droplets. As we get through that evaporator, we're going to blow our warm air that is warmer than our vapor temperature, and we're going to try to absorb some of the heat from our space, and we're going to assist that boiling process. Because remember, when I reduced that pressure at my metering device, I'm going to boil on its own. I don't have to have the heat from my space across that. It's going to boil. We're going to try to introduce some of our heat across that evaporator and absorb it and assist that boiling process. And as we pass through that evaporator, we're going to boil off all of our liquid refrigerant because that's where the work is happening. Our energy is being transferred in that expansion and contraction and that release of heat off from our refrigerant as we're boiling. That's where our work is happening. So if we have liquid leaving our evaporator, we're actually losing capacity on our evaporator. We need to boil off all of our liquid refrigerant in that evaporator so that we can make that evaporator as efficient as possible. But we have to maintain a amount of boil off in that coil so we can maintain some efficiency of it, and we can also verify that we have boiled all of that refrigerant into a vapor. So that is where we measure our superheat. So all we're going to do is make sure that we have a temperature coming out of that coil that is higher than the boiling point of the refrigerant. And we'll cover this more in depth as we dive into superheat and subcooling and talk about what's going on inside that coil. But we need to understand the fundamentals. We're verifying. Well, yes. Brian?
Nope, scratching my head.
Oh, never mind. Okay. So I've got all my cameras down at the very bottom so I can only see people's heads. So when we come out of that evaporator, we're going to be boiled off refrigerant. And then we're just simply going to measure it and make sure that we have completed that boiling cycle so that we've made our coil efficient and we have gotten rid of all of our liquid, because liquid refrigerant is an incredible solvent when it mixes with oil. If we get liquid refrigerant back to our vapor pump, we're going to do destruction in one of two places. We're going to destroy our pump, or we are going to destroy bearings in our motor. Because remember, a compressor is a two-part assembly. It's a motor driving a pump. So we can actually, if we understand what's going on with that refrigerant coming into a compressor, if I have a compressor that is not functioning properly, I can actually start looking at that and decipher between the two components to see if my motor is having a problem or if my vapor pump is having a problem. So if I take that whole principle of refrigeration and I look at that as, well, okay, so that is an AC system. That's what we typically encounter. What if it was a commercial ice machine? If it was a commercial ice machine, I may not be moving air across my condenser. I could have a tube and shell heat exchanger with water, city water passing through that, and I'm removing the heat out from my tap water and just sending it back down the drain. It's the same principle, right? I'm just moving heat across my condenser. On my evaporator coil, instead of moving air in the air conditioning system, what if I'm pumping water from a trough and recirculating that over that evaporator coil? I'm still transferring heat. I'm actually removing heat out of my water to assist that boiling process until my water gets down below freezing, and then I have a slab of ice on my evaporator. If this was a automotive air conditioning system, I still just have a vapor pump. It's driven by a different locomotive force. It's not being driven by an electric motor. What's it being driven by? A serpentine belt or a V-belt. Yeah, we're just using a different locomotive force to drive our vapor pump. And we're going to send that vapor pump, we're going to come right out of that pump, right into a condenser coil that is sitting in front or behind our radiator. And we're going to use our engine cooling fan to move that air across our condenser coil. We're going to come out of that condenser coil, we're going to go into a metering device. It's either going to be a piston or an expansion valve, and most vehicles in today's world use expansion valves. Some of the newer high efficiency luxury vehicles use electronic expansion valves. So we come out of that metering device, we go into an evaporator core that is sitting in front of our heater core in our dash and in our ductwork. And so we use the circulating fan of our cabinet to pass air across our evaporator core that is sitting right next to our heater core. And then we boil off the refrigerant in that core and we bring it back to our compressor. So even in the winter, when we are running defrost in our vehicle, we are running hot antifreeze, hot water through our heater core to maintain the temperature in our cabinet, but we are running our compression system so that we can remove moisture, because it's going to collect on our evaporator, just like a residential air conditioning system. We collect moisture on our evaporator to get it out of our system, right? If I have a moist cabinet in my vehicle, how do I get rid of the moisture? I turn my air conditioning system on. And if I'm not comfortable, I turn my heat on to compensate for that. But we truly have the exact same compression system in every refrigeration system. So if we take away that stigma of understanding that refrigeration is refrigeration, take away that stigma that other types of equipment aren't the same as what we work on, it will help you understand the entire world that you work in. So be thinking about that as we go through this class, is that just because you're working on an air conditioning system does not mean that you're not a refrigeration technician. You are a refrigeration technician in the HVAC industry. And so you should be able to understand what's going on inside that compressor in every application. So if we look at how a compressor is designed, compressors are designed with a compression ratio. And so compression ratio is the technical expression for a pressure difference. It's the high side absolute pressure divided by the low side absolute pressure. And remember, with our gauges, when we zero our gauges, we're doing what? We're zeroing to atmospheric pressure. So we have to adjust to be able to get to our true absolute pressure, not atmospheric pressure. So if a compressor has a high compression ratio, it can lead to overheated compressor oil. And it can, I'm gonna move my screen a little bit here. It can cause overheated oil, can turn to carbon and create acid in the system. We all know that. If we overheat our oil, we're going to break it down. And when compression ratios are high, more energy is needed to raise the pressure of the suction gas to the discharge pressure. It'll do it because it's designed to have a certain compression ratio. It's just going to utilize different amount of energies to maintain that if my compression ratio starts getting out of whack because of my conditions. If I look at a internal combustion engine on our vehicles, our motorcycles, or anything that we drive, we build those engines to a specific compression ratio. And that compression ratio allows us to monitor the conversion of pressures and horsepower. So if we increase the compression ratio on a compressor, it takes more energy to operate that thing, which is why we have to use a higher octane fuel on a higher compression ratio engine. It kind of gets into the same scenario when we think about the mechanical force that's used on our compressors. If I have to produce a compressor with a higher compression ratio, it's going to take more torque, more energy to run that thing. So if I change the compression ratio on my compressor, on my vapor pump, it's going to change the amount of torque that's required to keep that thing running at a certain RPM. So a lot of times when we get into higher compression systems, we'll actually end up using two compressors to do that, so that we don't just have one compressor with a high compression ratio. So if we get into a cascaded system that has two compressors, we're going to use one compressor. Say in this particular situation, we would have one compressor that has a 5-to-1 compression ratio to it, right? So we're going to come in with the pressure and we're going to compress it 5 times. So we're going to take a volume, we're going to compress it, and by compressing that 5 times, we're going to increase our pressure from 20, like this particular instance, from a 21 psi to a 100 psi. Well, then we could take that 100 psi and run it into a compressor that has a 1.7 compression ratio. So we're going to bring in 100 psi, we're going to now step it up to 170 psi, and it didn't take very much energy to do that. Our 5-to-1 compression ratio compressor took a significant amount of energy, but that 1.7 didn't take a lot of energy because it was only moving up 1.7. If I had a single compressor that was an 8-to-1 compression compressor, it would take a significant amount of energy to keep the momentum inside of that compressor. So I know most of you guys don't encounter two-stage or cascaded compressors, but I want you to understand the effect of compression ratio as we move forward, and just to see how it affects the electrical consumption of our compressors. So if we look at the compression ratio, and so assume that the same refrigeration system is operating with R134A as the refrigerant, and the same condensing temperature of 125 degrees Fahrenheit. So it has an operating pressure, put our gauges on, it's got an operating pressure of 184.6, and an evaporator temperature of minus 16 degrees Fahrenheit, right? And the compression ratio would be, so we think, well, does it matter? Well, why are we even looking at compression ratio? Well, we want to look at compression ratio to see how efficient my pump is actually running. So what I would do is, we know that to go from gauge pressure to absolute, we have to increase, our 14.7 roughly, to get our atmospheric adjustment so that we get absolute pressure. So we assume that the operating pressure is 184.6 on our high side. All we're going to now do is take our high side pressure plus that 14.7, and then we're also going to make our adjustment on our evaporator side, our low side. So this one's actually in inches mercury, so it's a little bit different conversion, but we're going to take the gauge pressure, since that one was operating in 0.7 inches of vacuum, we're going to do our 29.92 minus our 0.7, divide that by the 2.036, so that it gives us our actual ratio between our discharge and our suction. So if we look at that compressor, and we know that if we took 184.6, we had the 14.7, we're going to have, a 199.3, and then we're going to have a 14.34 on our suction side. That gives us the actual compression in our vapor pump. What's going on inside our vapor pump? So I would have, on that particular situation, a compression ratio of around 13.89 to 1. Now people say, well, why do we even, are we going to add that to our service? Probably not, but it helps you understand how efficient your pump is actually running. Let's use this same principle. So that was a low temperature, low pressure R134A system. Let's look at it in our world, and let's look at what our compressors are actually doing. So we're going to take, on this system, we're going to look at an R22 system, right? So this is a comparable operating 3-ton 13 SEER units. So I'm simply going to put a R22 3-ton unit up against an R410A unit, and I'm going to compare them, right? So I have an 85 degree outdoor temperature, I have an 80 degree indoor dry bulb, and a 67 degree indoor wet bulb. I've got my blower set at 1200 CFM, and I have a temperature differential split of 21 degrees on both of these systems. So either one of these systems installed in-house are going to be performing at 3-ton capacity. So if I look at an R22 system, so I use this same compressor, right? I'm going to use an R22 refrigerant in it, and I'm going to be operating at 218 psi on my high side. So I put my gauges on. I've got 218 on the high side and I got 80 on my low side. So if I want to go ahead and just convert my gauge pressures over to absolute, I add that 14.7. So I take my high side plus 14.7 and I divide it by my low side plus 14.7. So that would give me 232.7 divided by 94.7. I have a compression ratio on that compressor of 2.45 to 1. Okay. If I take the exact same situation and I have this system running on R410A, I put my gauges on it, and I've got a 294 pound head pressure. I got 126 pound low side pressure. I add my 14.7 to both of those. I have 308 on my high side. I have 140 on my low side. I now have a compression ratio of 2.19 to 1. And go, what does that mean? I have two operating systems, identical systems that are operating with different refrigerants. And I take a measurement of my pressures and I find out that my compression ratio is lower on my R410A because of my ability of that refrigerant to transfer heat properly, right? What does that tell me about what's going on inside of my vapor pump?
Working as hard.
It's telling me it's not working as hard. That's exactly right. So if my vapor pump is not working as hard, what does that tell me about my motor that's driving my vapor pump?
It's using less energy.
That's exactly right. So when we start talking about compression ratios, it helps us break apart our compressor and understand what the entire unit is doing based on its two components, its motor and its vapor pump. So if we're talking about, tin can compressors, either reciprocating or scrolls, we really don't have the ability to do a lot with that vapor pump, unfortunately. But it helps us as a technician to understand the efficiency of our operating system. If this was a different application and I was talking about, like a semi-hermetic, 3D, 4D, 6D, 8D Copeland compressor, well, then I could look at, if I have a compressor that's not operating properly, I can see what my compression ratio is. I can see what the current draw is on my compressor. I could also shut my system down and check the continuity across my windings. And if my motor is good, but my entire system is running at low efficiency, don't I have the opportunity to go, well, maybe I've got a vapor pump problem. Instead of replacing this compressor, how about I tear this apart and put a new valve plate on it and get this thing pumping properly? So it just changes our perspective on how compressors are designed and why we're changing compressors and working with refrigerants, because as we start using these other refrigerants, as we were talking about over the last two classes, as we have to find these refrigerants that are going to try to meet in that middle, to find that happy place between cost of production, cost of use, cost of manufacturing of the equipment, environmentally friendly. There's a lot of factors that goes into play. And one of them is the efficiency of a refrigerant. So we could have a refrigerant that is inexpensive to manufacture, but it might not perform very well. And if it doesn't perform very well, it's going to end up affecting our compression ratio, which is going to end up affecting the amount of current on our motor. So it just gives us an opportunity to understand that different refrigerants can affect the way our pump is operating. And we all want to look at that, is that we have a pump attached to some type of a locomotive force. Typically, we're using electric motors in our industry. All right, so there are kind of 5 types of compressors used in refrigeration and in the air conditioning industry, and we want to kind of brief over those. So we're going to talk about reciprocating compressors, which some of you younger guys to the industry may not even be familiar with a reciprocating compressor. Us old fogies who have been out in the field for a long time, that's all we knew up until a scroll came around. It was a reciprocating compressor, and I want us to dive into that and understand what that is, because there are still reciprocating compressors out there. You know, they're getting fewer in between, but you know, they are around. Most of your residential refrigerators, you know, the entry line refrigerators still using reciprocating style compressors. You know, light duty refrigeration is using reciprocating. I'm not aware of too many reciprocatings in our unitary equipment, but there could be. We want to talk a little bit about screw type chillers, you know, commercial compressors. We want to talk about rotary and scroll, because there's a big difference between the two of them. We want to look at that. And we want to talk about centrifugal compressors. You know, centrifugal compressors are used extensively for very large air conditioning systems, but it is our world. If you're working on large industrial and commercial HVAC systems, you can encounter any of these compressors. And it's good to know how they're designed and what kind of compression ratio they run at, because it's all about the efficiency of them. So if we talk about reciprocating compressors, they're categorized by their housing and the drive mechanism. So the two types of housings are open and hermetic. And probably most of you have not seen open drive compressors, or you haven't worked on them. I have. And I've actually got one sitting next to me, and I'll show you some pictures probably in our next presentation. You know, hermetic, when you hear the word hermetic, it refers to the type of housing that contains the compressor. So it can either be fully welded, it could be serviceable, or it could be truly semi-hermetic, where they completely rebuild them. And if you've not been to like a Copeland tear down class where you actually take apart a compressor, man, it is so worth your while. And hopefully Don will kind of brief on those classes on Friday. Just a fantastic opportunity to understand the internal mechanisms of those and how they are completely rebuildable. Just like a vehicle engine is completely rebuildable, our larger semi-hermetic compressors are absolutely rebuildable. And then a hermetic compressor has a direct drive mechanism that drives the compressor and motor inside the compressor shell. So we'll look at those. All right, so looking inside a hermetic compressor. So the unit's sometimes called a tin can. Most of us are familiar with the term tin can because it cannot be serviced without cutting open the shell. You can't get to the thing because it's completely welded. The motor and the compressor are contained in the shell, cannot be filled serviceable, so they are scrap compressors, and they're considered to be a low side device due to the suction gas venting. And either pressure lubricated or splash. It just depends on the actual compressor itself. I'm gonna see if I can blow this up a little bit without getting it too distorted. All right, so if we look at the internals of that compressor, this is what you would have seen in residential air conditioning systems up until scrolls. This is what you would have seen in all of your package units, commercial units, and we still see some of these large tin can applications in commercial stuff. So if we think about what was going on there, so we know that any compressor is a vapor pump. In our compressors, we use an electric motor. So this is a permanent split capacitor motor, remember, because it has a capacitor that drives it. So we have two windings on that motor. We have this particular one has a hollow core crankshaft, because remember, it's going to have typically a bearing at the top and a bearing at the bottom. So we've got to have a way to get oil to our bearings. We have a very heavy duty lower bearing assembly. And that got all crazy. And we have that crankshaft turning a connecting rod that is operating a piston. Kind of looks like a little single cylinder vehicle engine, doesn't it? Well, it's the same philosophy. A reciprocating engine is a reciprocating engine. We're just using it to compress vapor in this particular situation. That's what a vehicle engine is doing. We're compressing vapors, right? We're going to introduce oxygen and fuel. We're going to ignite it, and we're going to compress it in a compression stroke. Well, that's all a reciprocating compressor does. The exact same thing. We just use vapor in and vapor out. So with that compressor, we're going to bring in our vapor. Our suction vapor is going to come into the shell. We're going to use that vapor to help cool our motor, because remember, that motor is going to generate some heat. All motors generate some heat. So we're going to use that vapor to help cool our motor. This is another instance of why we cannot get liquid into our compressor. Even on this reciprocating, if I get liquid introduced into that, What happens if I get liquid refrigerant on the windings of my motor windings? Remember we were talking about in our motor class, yeah, we're going to destroy the insulation on our motor if we get liquid onto that insulation. If we get liquid into our bearing, we're going to have problems. If we get liquid into our oil in the bottom, we're going to get a problem with lubrication on our lower bearing and on our crank, right? So we cannot get that liquid into our vapor pump. So we're going to bring vapor in, it's going to pull it into the cylinder, our piston is going to compress it, and we're going to now discharge that out as a high pressure vapor. So pretty simple design, really, and that's why they lasted forever. You know, a reciprocating compressor, when properly operated, lasted for decades. So very good compressor to have. The downfall of those is they weren't the most efficient things. You know, they ran and they ran and they ran. They produced a lot of heat, but they weren't incredibly efficient. So as we started looking at new ways to make our HVAC systems more energy efficient, because we all know that our national energy grid is capping out. You know, we have to do a lot of infrastructure in the United States to increase our electrical grid, and we want to reduce our energy consumptions like the rest of the world has been focusing on for years and decades. So we started looking at new technologies and alternative technologies to reduce the energy consumption. So in that, we found other types of compressors, and we're going to really get into that in a minute. If we talk about
hold on
that,
1 second.
Yeah.
I got to mention a comment on that real quick. So the efficiency on that compressor, when you think about it versus a scroll, where the scroll plate is rotating in a circle the entire time. You said the compressor efficiency on this is not as good as some of the other ones. Think about that piston. That piston has to move up and back. So 50% of the compression cycle is on the compressor going the other direction, where it has to go back to cycle it back up, versus a scroll that is continuously going in one direction.
Yeah, absolutely. And when we talk about that
Straight
scroll, it'll help see that. You'll help see where we have positive and negative pressure in that pump at all times. And so, yeah, the pump itself, that's when we start talking about compression ratio. It really is a lot to do with the efficiency of our pump. If we talk about semi-hermetic compressors, they physically are going to be a larger compressor and much more heavy, but they're a phenomenal piece of equipment. So, it is a serviceable compressor. You can do internal workings on it. So, you can tear it apart. You can put new motor windings in it. You can put new cranks and bearings. You can replace valve plates. In the field that I came from, I was rebuilding these routinely. When I was doing maintenance on my compressor, my refrigeration racks, I was looking for compression ratios on my individual compressors to see if one wasn't pumping properly. And then if it wasn't pumping properly, then I would, verify that by doing a pump down process. And typically I would have a valve plate that was bad. And I'll show you what those look like. So these are very serviceable. The thing with a semi-hermetic compressor is that we still have the same philosophy, right? So if I look at this here would be a 2D compressor. It has 2 pistons. If I look at a 4D compressor, it's a V4. If I look at a 6, it's 6 pistons. If I look at an 8, it's 8 pistons. So it truly is a automotive style engine with a significant amount of friction inside of that compression ratio. So a lot of the heat that is being generated from our compressor in any type of reciprocating compressor is the friction of our pistons inside of those cylinders. So we have a significant amount of heat being generated. All right, now if we talk about an open drive compressor, most of you guys aren't going to encounter these, but I want you to understand what they are. So open drive compressors are manufactured in two styles, either belt drive or direct drive. And any compressor with a drive on the outside of the casting must have a shaft seal to keep the refrigerant from escaping to the atmosphere. And if you take one of our EPA classes, that's one of the things we talk about is that shaft seal on an open drive compressor. So open drive compressors are bolted together and they may be disassembled for servicing. So they're very much like a semi-hermetic compressor. They just don't have the motor on the inside. So there's a couple common designs of open drive compressors. So the one on the left would be your belt drive compressor. So it uses a separate, typically electric motor to drive it, and it's going to have belts. We also have one that the motor bolts directly to the front of it. And while this technology might seem like it's antiquated and out of date, it is not at all. If any of the guys from AK Steel are online today, they can vouch for that. They've got some of these in service today that are 20 and 30 ton or 20 to 30 horsepower compressors that are driven by 20 and 30 horsepower 3-phase 460 volt motors that are coupled directly together. So the electric motor sits right in front of that, and it just connects with a coupler to that pump. If we talk about automotive air conditioning systems, aren't we talking about an open belt drive compressor? If you look at a vehicle that was built before we started using the AC Delco style compressors in the 1970s and into the 80s, if you look at a air conditioning compressor on a vehicle from 70 or back, you're going to pop the hood and you're going to see that on the left-hand side.
Mm-hmm.
And it's an interesting thing to see. You open the hood and go, man, look at that big old chunk of cast iron. But they were a completely rebuildable compressor, so they had a very long life. The compressors typically didn't, go out on those. It's a good piece of equipment.
Clifton,
So yes,
your evacuation pump, direct drive.
bam,
We
absolutely.
all got
Same
those
philosophy.
sitting in our truck, so we're more used to seeing it than we think we are.
Yeah, I mean this technology really isn't outdated. It's just it looks different in different applications. And that's really what we're here to do, isn't it? We're just here to talk about the technology we have and understand what it really is. Because when we understand what it is, doesn't it make it easier to figure it out? I mean, we're all here to fix things, really. So the more we understand about the items that we encounter, the more efficient we're going to be as technicians. If we look at rotary screw compressors, so I'm sure you guys have heard the term of screw chillers or screw compressors before. May not have worked on them. I've worked on quite a few of these things. The rotary screw compressor, it's a different method of compressing refrigerant gas. So it's still just a pump, isn't it? It's bringing in a volume of vapor and it's squeezing it down so that by the time it gets to the end, it's been compressed. And that's all that we do. Anybody ever paid any attention to what a supercharger on a vehicle looks like?
Oh yeah.
Here it is. Same philosophy. All we're doing is we are driving a vapor pump. It brings in a certain amount of air and it compresses it down. So a vapor pump on a vehicle, it's driven by the RPMs. The more RPMs, the more your pump is running, the more pressure that you're increasing, right? That's all we do with a screw chiller. It is an inner vane vapor pump, and that's all that it is. So even though this thing could be the size of this room I'm sitting in, it's just a big vapor pump being driven by an electric motor typically. If you get onto larger applications where, say, if you're on a cruise ship that's using a rotary screw compressor for its air conditioning refrigeration system, what's it being driven by? Great big monster diesel engine. Same thing. The locomotive force that we use to drive our pumps can be different, but our pumps are just pumps. So inside, if we were looking at those reciprocating style compressors, the crankshaft of a reciprocating compressor transmit the circular motion of the rods into a back and forth or a reciprocating motion for the pistons. So the off-center shaft normally has two main bearing assemblies, one on the motor end of the shaft and one at the ends. And so those bearings are normally the larger because it carries a greater load on that system. So we have very significant bearings that are on those. Think about the weight that we're actually moving on that crankshaft. If we think about that centrifugal motion, that reciprocating motion that our electric motor is having to turn, that is a pretty significant amount of weight on its own, just on the crankshaft, let alone that connecting rod and the piston that it has to move. So we're losing some of the energy of our electric motor just by the weight of our rotating assembly. If we get into building high efficiency, high RPM, high compression ratio automotive engines, one of the main things that we do is try to reduce the weight of our internal reciprocating components. We want to reduce the weight of our internal structure so that we can increase the efficiency of our engine, the part that's driving it. So the connecting rods connect the crankshaft to the piston. So one fits the crankshaft with off-center throws, and the other fits the eccentric crankshaft. So on a two-cylinder, we're just opposing. The piston is the part that moves up and down in the cylinder. Piston is exposed to high pressure gases during compression, and during that upstroke, the pistons have high pressure gas on top and suction on the bottom side of it. If we look at other components, like if we were, say we're going to look at a semi-hermetic compressor. So the refrigerant cylinder valves control the gas flow, and so it could be on a tin can, any type of reciprocating. We have some kind of valve in there that is a moving component, right? So the valves control the gas flow in and out of the cylinder. It's controlled, it's self-actuated, so the gas pressure is controlled in, and outlet valves, they're being operated by pressure, but they also have, a permanent mount to them. So they're mounted onto a plate of some type, and then they're just, they're moving, they're functional components of that system. So we have another place for wear. So if we think about, if we are on that valve plate, like here's my valve plate on the left-hand side. Let me grab that Sharpie. If we look at those valves, here is your actual valves, right? So we have holes underneath of those that our vapors come through as we're pumping. If you think about those valves, think about how many times those things are opening and closing. On every rotation, those things are opening and closing, opening, closing, opening, and closing. Eventually, we're going to stress that steel, aren't we? Over time, we're going to stress that steel and it might not close properly, or we might get a piece of debris in there, and that snapping process will take that piece of debris and crunch it into the surface of our valve plate. And so then we lose some of the pressure that our pump is producing. That's how we can look at compression ratio and go, hey, my compression ratio is way off. I don't have much of a differential pressure here. I'm supposed to have a 2.5 to 1 compression ratio, and I'm running 1.6. And my refrigerant charge is proper, everything's running fine. What's my problem? My vapor pump. I'm not producing my compression ratio in my vapor pump. So there's different styles. There's pop-up valves, there's reed valves, there's depending on the manufacturer of the compressor, there's a variety of different applications, but they are all mechanical operated valve assemblies. Sometimes we do add, like mufflers to a system, so that the head of the compressor holds the top of the cylinder together. It often contains a suction chamber, which is separated from the discharge chamber, and then a lot of times we'll use mufflers to aid in that pulsating sound. So if you think about those valves, like if we have a 1-cylinder or 2-cylinder compressor, every time I'm in between, I've got of all my valves. So a lot of times we'll add a muffler to that system to help just balance that out. Just like we use a muffler on a vehicle to quiet things down, we'll use a muffler to help quiet down and smooth the actual sound of our operating system. Doesn't really affect the performance of it. It just maintains a more even sound out of that thing. And then we'll have a housing, and we'll have our internal motor, and if it's an open drive, then we have a separate seal on that thing, our shaft seal. So if we look at the belt drive on a open drive system, the drive pulley can be adjustable, which allows the compressor speed to be adjusted. So if we look at a reciprocating compressor, when my motor is running, I'm applying voltage to my motor, I have that motor connected directly to a crankshaft, it's going to turn whatever RPM my motor is running, right? Well, with those open drive compressors, we could actually change the capacity of our compressor based on the drive ratio. So those of you that work on commercial air conditioning products, this is going to make a lot of sense to you when you're talking about belt-driven pulleys on our blowers, because this is how we can actually calculate the speed of that thing. So let's say I have a motor. So I'm working on a open drive, a belt drive compressor, or I'm working on a AC blower, same philosophy. I have a motor that is running 1725 RPMs. That's a pretty common RPM of our motors, right? And a drive pulley of 4 inches is used to drive the compressor, but the compressor is only going to turn 575 RPMs. It's got a pulley size 12-inch, right? So it is desirable to reduce the compressor speed to 500. So say the capacity on this system is more than what I need, and I want to reduce the capacity on this system. And I need to get my RPMs from 575 down to 500. What would the new drive pulley size be? So we get this in the AC mode. If I have an AC system that I need to turn into a dehumidification system and reduce my airflow from 450 to 400 or something, how can I figure that out? Well, it's the exact same way that we figure out the compression on our compressors. So you take the drive pulley size times the RPMs. We can put that into a factor. So if we have pulley 2 and RPM 2, and we have RPM of 1, so we know the pulley 1 pulley size, we know the RPM of our motor, and we now have the RPM that we want our compressor to run. We just simply plug in some numbers. So if I have a 12-inch pulley on my pump and I want it to run 500 RPMs, and my motor runs 1725 RPMs, I just simply do the math. I plug that in and it factors out to 3.48 or a 3.5 inch. So all I had to do was go from a 4-inch pulley, which gave me that 575, and now I can put a 3.5 and I will actually get 500. So it's an exact calculation of RPMs. And that's what we used to decide the capacity of our compressor. Because remember, if I have a open drive compressor and I want it to pump more, I just run it faster. If I wanted to pump less, I just run it slower. So that's belt drive formulas, which is good for airflow as well.
Can I jump in for a second?
Yeah, absolutely.
Just a thought too. Then with efficiencies and everything, the closer you are to a 1-to-1 ratio, the more work that the motor is going to do, and the more differential. So I guess to bring it home, my point is, think about a 10-speed bicycle. You have all the different gears and the different ratios from the front gear sprocket to the back gear sprocket. And if you're on a 1-to-1 ratio, you have to pump really hard to get that bicycle going. But if you change the ratio, yeah, it makes it a lot easier for you to pump to get the same RPM.
Does. Absolutely. If we look at characteristics of direct drive compressors, the direct drive compressor is limited to the motor speed. In this type of application, the compressor and the motor shaft run end to end. So the motor and the compressor shaft must be perfectly aligned or the bearings will fail prematurely. Because remember, that motor's running 1,725 revolutions per minute. If my coupling between the two of those is not centered perfectly, I'm going to have a problem. So if you're working on any of this larger commercial and industrial applications that has a direct drive, so a vapor pump sitting in front of an electric motor, we have to make sure that those couplers maintain their integrity. So efficiency is determined by the initial compressor design, so our compression ratio. Efficiency starts with the filling of the cylinders, and then 4 processes are going to happen. So this is in our reciprocating compressors. We're going to have an expansion, a suction, intake. We're going to have a compression cycle, and we're going to have a discharge cycle. So what happens in that process? What happens if we get liquid in a compressor can be a problem from more than one standpoint, like we were saying earlier. You could have liquid slugging, which would cause intermediate damage to our components. Small amounts of liquid flood back can be just as detrimental, but may take more time to cause damage. In these reciprocating compressors, so over time, because we're now going to have different temperatures across our compression components, and marginal oil pressure can cause the compressor to throw a rod. So if we think about that, if we're introducing refrigerant into that oil and we're going to cause that oil to foam, our oil pump is a liquid pump, right? It's not a vapor pump. So in these reciprocating style compressors, our oil pump is designed to move liquid oil, not vapor. So when we get that refrigerant boiling inside of that oil, we're actually going to foam our oil and we're not going to maintain our proper pressure. let's skip through a little bit of that and get to our, here we go, yeah. So we won't get into our actual process inside of a reciprocating compressor, because I want to make sure we have enough time to cover our other newer style compressors. So the piston in the highest point in the cylinder, so it's top dead center. Both the suction and discharge valves are both closed. The cylinder pressure is equal to the discharge pressure, and as the crank continues to turn, the piston moves down inside of the cylinder, and the volume inside the cylinder increases, right? So we're going to come in on the suction valve. As we're sitting there, both of our valves are closed at top dead center. As we move our piston down, we're going to fill that cylinder, and we're going to bring our pressure in. Then as the piston moves down, our pressure decreases, the cylinder pressure falls below its suction pressure, the discharge valve remains in the closed position for a point, and as the piston continues down, vapor from the suction pulls into the cylinder, okay? So our valve is going to open on our suction side of our plate, and it's going to try to maintain closed. So think about the amount of pressure on the back side of those valves. There are a lot of tension on the valves on a reciprocating compressor, a lot of mechanical motion there. And then as the piston starts to move up in the cylinder, the suction valve closes, the discharge valve remains closed, and because it's maintaining that compressed ratio, right? And then as the piston moves up, the volume in the cylinder decreases and the pressure of the refrigerant increases. So we're going to have that volume on top of the piston. Then when the cylinder pressure rises above that discharge pressure, whatever that point of release is on our valve, the discharge valve opens and the suction valve remains closed. So we're going to allow that pressure to release on our discharge side. It has now been compressed in our compression cycle. If we look at the function of that, it's simply going to fill the piston. We're going to bring volume into our chamber. We're going to compress it, and then we're going to discharge at a higher rate. So that's just the simple process of compression ratio. Some of the technology that's changing in our compressors, new technology makes it possible for real-time monitoring and keep an eye on the operating conditions of our compressors. So we're starting to see a lot more controls to be able to maintain our compressors. Now, if we take that philosophy of compression ratio and all of that energy that is being exerted inside of those cylinders and on that piston and on that connecting rod and on that crankshaft, well, it's being driven by a motor. So if we could make the pump more efficient, in return, it should make our motor more efficient, right? So not only did we talk about refrigerants having an effect on our compression ratio and the efficiency of our compressor, well, now we're going to look at a pump that can increase the efficiency of our compressor because it's going to have less mechanical components. It's going to have less centrifugal weight. It's going to have a balance on the compression cycle so that we don't have a large amount of force being exerted on our motor. So how a scroll is designed, it has two spiral-shaped scroll plates, and those plates, they're involuted spirals. So you have one spiraling inside of the other. So one is a stationary, one is an orbital. If we look at what is going on inside of that compressor and we compare that to a reciprocating compressor, we still have an electric motor, right? And if we're talking about a standard single stage or two stage compressor, scroll compressor, it's still a permanent split capacitor motor driving our pump. All right, so we have a capacitor for that because we have two windings on that. So motor wise, on a standard scroll, we've not really increased the efficiency of the motor. We've just increased the efficiency of the pump, which in turn caused our motor to use less current. So we're going to use another hollow crankshaft running through the center of that because we need to get some oil up to our upper bearing, right? Because it's still a crankshaft. It's still it's still rotating as one entire assembly. So most of our weight and most of our pressure is being exerted on that lower bearing, but we do have an upper bearing. So we have a hollow shaft and we're going to lubricate that bearing. So we're going to turn our pump so we have our stationary scroll on top, and then we have a orbital scroll that is connected directly to our crankshaft. So really all that our crankshaft is doing is turning that one orbital scroll plate. So we don't have all of that kinetic motion of a heavy crankshaft with journals and bearings and connecting rods and pistons and friction inside of a cylinder. So we've significantly reduced the amount of friction inside the compressor, which in turn reduced the amount of torque needed by my motor. So we had a combination of things going on to make these scroll compressors so much more efficient than what we've had in the past in reciprocating compressors. Gotta move my screen around. Maybe. So inside of that vapor pump, here's what we're actually doing. We have multiple compression processes going on all at one time. So our actual entire scroll maintains a fairly evenly distributed pressure along its entire surface. And how we are doing that is in that multiple compression stroke. So we're going to bring in our vapor, right? We're going to bring suction into this portion of our scroll plate. So a large opening at the entrance, and it diminishes as it gets to the end of it. As we rotate inside that motion, we're now going to close off that part, and we're going to push our vapor further inside of that rotational cycle. As we move along, see now, as this vapor is passing through this portion of our compression, we're now reintroducing pressure over on this side. And as we move along, we just keep doing that. We move it along so that we not only have one compression in a revolution, we have one here, we have one here, and we have another one out here. So we have multiple compression cycles going on inside of this pump. And so instead of just having that positive and negative displacement on the reciprocating compressor, we now have fairly even distribution across our pump. So our centrifugal motion isn't offset. Because if you think about that, if I've got a 2-cylinder reciprocating compressor, I have all sorts of momentum going back and forth, right? Which is putting a lot of resistance on my motor. If I have multiple compression strokes inside of that compressor, I'm actually distributing it more evenly. So I don't have as much reciprocal energy going on as what I had in a reciprocating compressor. So a lot less energy to move our vapor pump. So, as we wrap up this part of it, just be aware that the main reason scroll compressors are gaining popularity over piston type is energy efficiency, reliability, and quieter operation. We have a lot less friction, we have a lot less electricity. There's no volumetric loss through gas re-expansion in a piston type compressor. The scroll compressor requires no reed valves, so we don't have those additional parts to fail and wear out. So it does not have valve loss. We have a separation of suction and discharge gases, so we reduce that heat that was transferred, and centrifugal forces within the mating scrolls maintain nearly continuous compression of consistent leak-free contact. So it's been a big change in our industry to see us going from reciprocating compressors into scroll compressors. And we do have some other types of compressors. If we want to spend a little bit of time talking about some of these centrifugals, we can. But I think I really want to move on to talking about some of the new technologies. So I'm going to end this slide presentation, and I want to bring up, I've actually got 3 here to cover. I'm just going to go into that Daikin one. Actually, we're going to I think we're going to start reducing these classes from 2 hours down to about an hour, hour and a half, somewhere in that ballpark. So I've had a lot of people that cannot maintain for 2 hours, and it is a lot of sitting, even for us. So we'll try to trim things down just a little bit. Let me get this presentation going, because I want to talk about the things that are going on in some other styles of compressors, in our rotary compressors, because we didn't talk much about the rotary compressors. And that presentation is a few years old, and rotaries weren't as popular as they are now. So, this is a Daikin presentation, but it's over rotary style compressors in general. So when we talk about rotary compressors, you know, rotary compressors have a different type of vapor pump to them. And if you've ever worked on a packaged window air conditioner, this view is probably familiar to you. You know, it is a common style compressor that we've used for a long time in smaller capacity systems. We're now really starting to use them in larger capacity. Daikin has been, you know, producing, you know, their swing compressor, which is a rotary swing compressor, you know, for decades. Well, they're now introducing it into a lot of their unitary products. And if we look at the function of a rotary compressor, there's some things to point out that don't always get talked about. You know, if we were looking at installation manuals for, just say, Goodman, if we read a Goodman installation manual from 10 years ago when it was primarily reciprocating compressors, the installation manual itself actually instructed you to open the suction valve on new installations first to balance the pressures in your system. When we talk about these style of compressors, we have to really think differently about that. Because if we look at just by the design of a rotary compressor, the rotary compressor is a little different shell construction than even the scroll, because, you know, the scroll had a suction typically on the side of the housing. With rotary compressors, we're actually bringing our suction in. We have a accumulator. Remember, we cannot get liquid into our compressors. But with a rotary, we're actually using our cool vapor to help cool that lower bearing assembly before we even start our compression cycle. And the thing with a rotary compressor of any manufacturer is on an installation, just think about that for a minute. On an installation of any outdoor unit that has a rotary compressor, if I open that suction valve first, what's going to happen to the oil in my compressor? It's going to get sucked out of it, isn't it? It's going to pull all of your oil out of your compressor and put it back into your system. So when you read the installation manuals, I mean, we always joke about installation manuals. Greg Millsap does this really funny video of in installation manuals and some of the things that they get used for other than being read for the installation of equipment. It's quite comical. And unfortunately, a lot of people do not read installation manuals for equipment. And I really want to stress this, because when we changed from reciprocating and even some of our scroll compressors into, we actually had an issue with some of our entry line equipment being locked rotor on installation, particularly our 13, 14 series entry line stuff. And so one of the things we started looking at was, well, why? Why are we having such a failure? Because these units are tested at the factory, they're well-designed pieces of equipment. And a lot of times it was contractor based that we would see many of these units having that problem. So I started looking at it as the perspective of why. Well, if we look at construction, it all goes back to why we are all here. If we understand the construction of something, we can better diagnose it. So we just simply started looking at that and went, man, if we open the suction valve first, which people have been taught in the past in Goodman installation manuals, then we would literally pull the oil out of the compressor and we would have a dry bearing on startup. And we went, wow. So we contacted our manufacturers and we got back to looking at installation manuals. They went, I guess we didn't look at that very well. Like, I don't think you did. So if you look at all of our new installation manuals for rotary compressor equipment, every one of the installation manuals now says, at least our manufacturers, now says, open that liquid line first, because of this right here. So be aware, if you have a rotary compressor of any brand, any piece of equipment on an installation, make sure you're opening that liquid line first and not that suction line. Because I had to prove this correct. I had an installation, contractor called me and said, hey, I just installed this brand new unit. I've got locked rotor right on the get-go. I was like, okay, I want to test something. Did you open the suction line or the liquid line first? He says, well, open suction line. I was like, okay. I explained this to him. I said, all right, so we now have no oil in our bearing. right? That motor is designed to turn that crankshaft freely. It's not a high torque motor. It's a permanent split capacitor motor. Go put a hard start on the thing, let it sit there for a while. Say, okay, I'll run to my local Johnstone. I'll go give me a hard start kit and I'll come back and see if I get this thing moving. I said, if it doesn't fire up, we're going to replace it no matter what. But just out of curiosity, I want to see if this is exactly what we are finding in the field. He calls me 45 minutes later. So he made a trip over to one of our ND East locations, comes back. He says, man, I got back here and turned that thing on and it fired right up. Everything's running perfectly. I was like, yeah. So our oil finally had a chance to migrate back into the compressor. He's like, who'd have ever thought? I said, well, a lot of us didn't actually think about that. It was something that we just found by doing these classes and talking to people and looking at how things are constructed. So understanding how something is constructed is a tremendous asset in our industry. Indiana does not have state requirements for licensing. So there are a lot of people that are installing that are just not educated enough. And that's why here at Johnstone, we're providing these classes for free to you guys. This is stuff that you learn in classes that typically would cost a lot of money. So we're trying to help educate you and understand the way things are designed. And yeah, it's a very good point. So if we look at what's happening inside of that compression stroke in a rotary compressor, it's similar to a scroll, but it's only doing a single compression, right? So it's pulling in a volume and it's compressing it in an orbital passage. What Daikin particularly found is, remember, it's all about increasing the efficiency of the pump. And if we can increase the efficiency of the pump, we can increase the efficiency of our motor. So consequently have a much more efficient compressor. So if we look at what's going on inside of a rotary compressor has a crank that is just turning this center cavity. It's compressing its vapor across the outside of the cavity. And then as it enters, it is using a blade that has a spring up here to keep force on this blade so that it maintains traction against the center of that compression device. I'm not even sure what they're calling that compression side of that. So we're going to constantly have friction across that point. What Daikin has done is they've redesigned that compressor, that rotary compressor. They've made this solid and used a pivot point up here. So we don't have the friction that was going on right here in a traditional rotary. So they took a design that was a very good design. Rotary compressors are, very efficient compressors. And they took that philosophy and they increased the efficiency of the pump, which in turn increased the efficiency of the total compressor. So a very nice design. Some of these are even a double, so we'll have two pumps going on at one time. So that's the internal cutaway of that compressor. So if we look at the standard rotary compressor, that's what's going on inside, constant friction. If we look at what's going on inside of the Daikin's redesigned, it's going to reduce that friction. So Daikin's the ones on the left versus the one on the right, which is a typical rotary. So it's changed the way that our pumps function. Another thing that they did was they increased the efficiency of the motor by increasing the strength of the magnets. So they went to neodymium magnets in the rotor, which are 7 times stronger than ferrite magnets. So increase the efficiency of the pump, increases the efficiency of the compressor. Increase the efficiency of the motor, and we also increase the efficiency of the compressor. The only other thing now that we can do to a compressor is change the motor, right? So if we really want to control capacity and we really want to control efficiency of it, can't we simply take out the permanent split capacitor motor and put in an ECM motor? That's really what we're doing. When we get into inverter compressors, all we are doing is taking that either scroll or our swing style compressor. We're going to take out the permanent split capacitor motor, and we're going to put in a commutated motor, a digitally commutated DC drive. So now we've increased the efficiency of our vapor pump, we've increased the efficiency of our motor, and we have went a long way from a high friction permanent split capacitor motor compressor assembly to a lower friction, which is high efficiency compression and high efficiency motor. And we don't know what that next stage is going to be, but I will guarantee you will see inverters in most of the things that you install in the next generation of equipment, because we have now affected that total capacity of our system based on performance of our compressor. So that's where we are compressor wise. Lots of new, lots of old still in the industry. But the future is absolutely in scroll, rotary, and ECM motors. So a lot of stuff for one little class. I'll go ahead and open up all of the lines. Anybody have any questions that they would like to ask about compressor technologies? And those of you like LCS that's enjoying that quietness of that new Daikin fit, now you can understand why. We have reduced the friction in our pump, and in return, we've added a very high efficiency commutated motor. So our friction is down and our energy consumption is down because of the companionship of a high efficiency pump and a high efficiency motor. Okay, well guys, I'm going to go ahead and end that for today then, and look forward to seeing you all on Friday. Don Gillis will be helping talk about some of the up and coming changes in compressor technology, especially like we're moving into like CO2 refrigerants and such. And we also have Flex Train Thursday tomorrow, which we're going to be talking about multimeters. So everybody have a safe day, and we'll see you later.
Thanks, Cliff.
Thanks, Cliff.
Mm-hmm.